Hi, all. Thank you so much for having me today virtually. I'm happy to be here, and I'm happy to talk to you a little bit about why it's important that we assess multi system effects of individual stress response in human spaceflight. I'm Dr. Malika Sarma, a postdoctoral research fellow at Johns Hopkins School of Medicine in the Human Spaceflight Lab. If we imagine for a moment that we are in the future, the year is 2045 and we have humans on Mars. Over the past several decades, we have orbited the planet, we've put rovers on the surface, we've taken pictures of the landscape and the sediment, but now we have taken living and breathing human bodies to another planet. Under these extreme conditions, we know that our bodies will be responding, and we can only guess how. Further, the shift from long duration flight in a microgravity environment to a new planetary habitat has an additional set of risks and challenges that need to be addressed. From an evolutionary perspective, our species has taken over a millennia to adapt to the many myriad environments here on Earth. But we have essentially put humans in a tin can on a bomb and dropped them off to a whole new planet that is decidedly not Earth, with some tools and some food, but we really don't know how are they going to acclimate and adapt to these environments. How do we make sure that we can keep them alive? This question can and is in the process of being answered from a number of different perspectives, taking engineering or medical or legal insights. However, as a biobehavioral researcher, my perspective necessitates me to look at how human bodies and behavior are functioning and interacting. I believe a key component is understanding the multifaceted and bidirectional radiating effects of an individual's stress response. The normal stressors experienced every day on Earth are shifted, some exacerbated and made larger, and others diminished, but they all have critical importance to human health, performance, and survival in a spaceflight mission. For those of you who have been attending several of these talks, you must be familiar with the 5 hazards of human spaceflight. I'd like to thank NASA's Human Research Program for providing these excellent illustrations. First, we have gravity fields. Both the gravity fields experienced in microgravity and in a different planetary or lunar environment, but also the shifting gravity fields. This will be affecting spatial orientation, hand-eye coordination, balance, locomotion, and bone loss. The second hazard is isolation and confinement. Isolation and confinement is related to a decline in mood, cognition, morale, and interpersonal interaction. It's also associated with circadian rhythm dysfunction and nutritional deficiency. Third is a hostile enclosed environment. Because any spaceflight mission necessitates that human astronauts travel in a built environment, there leads the risk to an easy transference of microbes and microorganisms from person to person. We know that it is related to stress hormone elevation as well as immune system alteration. The fourth hazard is space radiation. When in a spaceflight environment, you can encounter up to 10 times the radiation than experienced here on Earth. This can lead to damaged central nervous system, altered cognitive function, reduced motor function, and behavioral changes. Our last hazard is the distance from Earth. Communication delays and limited to no opportunities for resupply leads to psychological and physiological implications for being so far from home. If we look at NASA's path to risk reduction, we see that each specific risk is siloed into a separate category, or swim lane. However, there is a growing need to take an integrative approach to these different categories, since within any individual, these risks are layered on top of each other to create potential agonistic or compounding effects. Understanding, on one hand, how the many ways in which stress response is activated in a spaceflight environment, and on the other hand, the complex downstream effects of said stress response in one way is to take this necessary integrative approach. What is the stress response? The homeostatic model sees organisms' bodies as a responsive machine, acting like a thermostat responding to the environment. These responses occur over multiple timescales, starting with the well-known immediate fight or flight response, which includes the quick and immediate sympathetic nervous response, followed by a relatively slower hormonal release. Some of the things that can happen in the fight or flight acute stress response includes increased blood flow to the brain, increased production of catecholamines, including epinephrine, norepinephrine, dopamine, which can all help to facilitate cognitive performance. We see increases in heart rate, as well as increased blood flow to larger muscle groups. Digestion slows dramatically while blood pressure increases. A critical system driving hormonal or neuroendocrine response is the hypothalamic pituitary adrenal or HPA axis and its output cortisol, which can be very easily measured non-invasively. Cortisol is produced through the HPA axis, which works on a system of positive and negative feedback loops, responding to stressors from the environment. So, for example, how you spend energy in a negative feedback loop to overall hormone production means that the more intensive activity you're doing and the more energy you're spending, the less energy needs to be diverted to things that don't matter at that moment, including reproduction or digestion. So we know that within an individual, the stress response has both cognitive and physiological outcomes. Now, what is less studied is how the cognitive and physiological outcomes may impact each other, especially as environments change. When we think of the human capacity for adaptation and survival, we know that here on Earth, humans have successfully responded to a variety of stressors over a multitude of timescales and landscapes across a range of environments and ecosystems, from high-altitude environments to desert environments, to extreme cold, like in circumpolar regions, to environments that are resource abundant but with high parasitic and pathogenic loads. The key thing about humans is that we have the ability to flexibly respond to and adapt to a wide variety of stressors that we may encounter. Each of the 5 hazards, gravity fields, isolation and confinement, hostile enclosed environments, radiation, distance from Earth, exerts unique acute and chronic stressors on the body. As the body is responding to these challenges, it leads to further changes in physiology and behavior. Spaceflight is not an easy environment. Researchers and medical professionals have been working over decades to try and get a handle on what happens to the human body in these extreme conditions. Now, to clarify, we have to think of the human body within a human-built structure and the built environment within. We know that a spaceflight environment impacts the brain for both structural and functional changes, your cardiovascular system, your bones and muscles, your gut microbiome, among others. To make things more complicated, we know that all of these systems are affected, but an individual physiological or behavioral system does not exist in isolation within the body, or even between bodies. So changes occurring from stress specifically are compounded to the other changes that are occurring due to the shifting environment. They are all likely connected through various feedback loops which are vastly understudied, though there is recent interest to this kind of integrative systems approach. This complex interaction is key, and looking at something as broad-reaching as a stress response is a way to get at the integrative interactions. Do you see the tiny speck? That's Earth from Mars. It's also a good approximation to comparing what we do know about the possibilities of what will happen to the human body as we become a spacefaring species. So we're at right now is that science is hard. Biology in humans on a whole different planet is harder. What's the point of even trying to figure anything out if it's just too complex and complicated to bother with? Well, we have different ways to try and get at these questions. There's a famous saying that I like to use in all my talks: all models are wrong, but some are useful. So, what space models do we have? We have our existing data actually at spaceflight, from the Space Shuttle to Skylab to ISS. Even these stints at spaceflight are only models because time and physical space can really make things quite strange. But for the amount of research that needs to be done, we have to get more creative and think of other options. Right now, the best way to try and figure out what's going on is to use analogs. Analogs that we have include Hera, Parabolic Flight, Concordia Station, and Antarctica, but also expeditions. And today I'm going to talk a little bit of data that can help inform our understanding of the human stress response using an expedition analog. So I did some work with the National Outdoor Leadership School to look at perceived experience and stress response. The question we had was, does perceived stress predict greater cortisol? And what we find is that it does. Similarly, we want to know, does the experience of feeling resilient predict lower cortisol? And this too we found to be true. So when thinking about how social and group dynamics may influence individual physiology, we find that lower perceived stress and higher resilience predicts lower cortisol. Higher resilience predicts greater average energy expenditure as well. The key takeaways is that individual perceptions of their environment predict a cortisol response or a stress response. We are working on a series of upcoming experiments to address the specific moderating effects of stress response on team behavior and group dynamics, sensory motor function, and vestibular adaptation, as one way to better understand how these different facets are all connected to each other. But there's still so much we do not know. In fact, the biggest concern when preparing for a mission to the moon or Mars, or really any long-duration spaceflight, is not the known unknowns, but rather the unknown unknowns. The key is in the connection between systems and finding mechanisms, like the stress response, to evaluate these connections. Humans are flexible, plastic, and adaptable. The changes that we undergo in any environment as we respond to stressors are often our body's attempt to actually keep us going and alive. We just have to follow the thread. Thank you so much.